Okay, so we've seen the running time of Maxflow. Let's see what it involves, right? So you have the Ford-Fulkerson method. As long as you can find an augmenting path in the residual graph, you will augment it by some appropriate path, keep augmenting. So there is a certain time involved in constructing the residual graph and finding a path there. Okay, how much time does that take? Order m. You just need to figure out, for every edge you need to see whether it put it in the residual graph or not, right? If there is a residual capacity this side, you will put that direction edge, and if there is a non-zero flow this side, you put this edge. So that's order m time, and then finding a path, you do some BFS, DFS kind of thing, right? So each time you are spending order m for augmentation. So now the total time is take order m and multiply by the number of augmentations you do. Okay. So let's, the number of augmentations you do, so if your capacities are all integers, let's say, then this is clearly one upper bound, because m is the number of time for each phase, and assuming you increment the flow by 1 every time, you start with 0 flow, this is like a crude upper bound, not a very nice upper bound, because it just, the time depends on the value of the output. Okay. You can also say it is m times c, where c is summation capacity out of, right? If you look at your S and look at, you basically, I'm saying there is some upper bound for Maxflow. This is an upper bound, so I can bound by this. Okay? This is the capacity on these edges. And so now, again, even this is not so nice, because the time depends on the values on the input, and I would really like what is called a strongly polynomial time algorithm, where the running time depends only on n and m, the input size. You can improve this to m square log c. I don't know whether you saw this algorithm. You have seen this algorithm using some different kinds of augmentations. So today what we will look at is algorithms whose running time depends only on m and n. Okay. So the first such algorithm is due to Edmonds and Karp. And the idea is simply the Ford-Fulkerson algorithm says find an ST path in the residual graph. Instead, we are going to say find shortest path. That's all. That's the only thing we're going to do. So every time we're going to augment by. So for example, the bad example I was telling you the other day, some large numbers here, and this may be 1. Your augmenting path can be all the time something like this. So you will send a flow of 1 here, take it out, 1 here, take it out, kind of thing. But if you look for a shortest path, you will augment this way, and at least this example goes away. So you will just do some 2 augmentations in this example. And here we are going to argue that if you do this, then the number of augmentations and so total time right, because we already observed that between two augmentation the time you spend is to construct the residual graph and find the path. Finding the shortest path can also be done in m plus n time, right, because we're not talking about in the weighted graph, it's just in the unweighted residual graph. How do you find the shortest path, shortest ST path? BFS. Come on. BFS finds the shortest ST path, right? So just start doing a BFS from S. Okay, so this is what we want to prove. And this is proved using two claims. So let me do a top-down kind of thing. So claim one, or since I call this claim, I'll call this lemma. The shortest path length from S to V for all V in V minus S or including V never decrease. That after augmentations. So what do I mean by this? So you have your flow F and you construct your residual graph GF, and there is this path from S to V in GF, and then after some augmentation later on I have a flow F prime and I compute GF prime and look at the shortest path from S to V. What I mean is the length of the shortest path from S to V in F prime is greater than or equal to. That's what I mean by this statement, that as you move along, your shortest path length either remains the same or it just increases, it never decreases. This is lemma 1 we will prove, and using this we will show lemma 2. So before I show lemma 2, I need this notion of a critical edge. So what is a critical edge? An edge UV is critical in GF, let's say, in your residual graph, if it is part of the augmenting path and its residual capacity is the smallest in the path. Right? So every time you augment by shortest path, and I claim that this edge UV is a critical edge in GF or in critical edge sometime if it is part of this augmenting path. And how much do you augment the flow by? You will look at the minimum residual capacity and you will augment the flow by that time, and this edge happens to have that minimum residual capacity. Okay. There may be several other edges with the same residual capacity, but this is one of those edges. Then I call that edge as a critical edge. Okay. So the lemma 2, which we will show. Where it duster like the 30 it's pretty bad. Is that an edge is critical. So same edge can become critical multiple times, right? How does it become critical? So you do this augmentation, this edge was critical, okay? How can it become critical again? So what happens, so here is this flow and here is a ST path and you augment through that. This edge has become critical. So what happens in, let's say F prime is the next flow you get. What can you say about in F prime? What about the edge UV? What happens? It will be in the opposite direction. UV is gone, but it will be in the opposite direction, right? Because you are sending some flow through this edge, and this is saturated because it's critical. So UV edge won't be there. Okay. In GF, you could have edges in both directions in general, but in this case, since UV is saturated, because it's critical, it's saturated, it will be out. It won't be in this graph. But how can it become critical later on? How does it even surface later on, right? Right. So that there is some flow sent through this edge in this, this is part of some augmenting path, and so maybe, which means that you have reversed some edge, some flow. So this edge becomes, has a certain residual capacity that it will come back again, and in that augmenting path, it's critical. Right? The same edge can become critical multiple times. So an edge is critical, at most n by 2 times. This is the next lemma. Okay. Now do you see the claim from lemma 2? This is the claim we want to show. Huh? Because every augmentation has some critical edge, right? So you associate with every augmentation some critical edge. Now I am claiming that an edge can be critical at most n by 2, the same edge. So the number of augmentations possible is at most, m times n by 2, right? Because there may be many edges that are critical, that works in your favor actually. So, but you can sort of bound the number of augmentations by the number of critical edges, and that will be m times n by 2, and that's what I wanted to show, and this will imply that. Okay, so these are the two lemmas we want to show. All right. Okay, so let me just write that lemma 2 implies the claim. Okay, so now not very hard, but okay. So it just uses some properties of shortest path. Okay, so suppose not, okay, that, so you have a flow F, and here is the residual graph, and there is a vertex V. Okay, so at some point, yeah, so you do some augmentation here, and then you get a flow F prime, and in G F prime, it turns out that the length of the shortest path from S to some vertex V in F prime happens to be less than where F is the flow just before this happens. Okay, so suppose you look at some residual graph where for some vertex V, the length of the shortest path from S to V is actually decreased from what it was before. So before, so let's F is the flow before this augmentation. I want to arrive at some contradiction. Okay, so suppose df prime SV is less than df SV. So this notation means the length of the shortest path from S to V in GF prime. Okay, and suppose V is the closest vertex to S in GF prime with that property. Okay, so lemma on what we want to prove is clear, right? So we just want to show, we want to get a contradiction for this. Okay, so let me look at the shortest path from here in GF prime S to U to some V, and the path goes like this. And it turns out that this length from S to V has actually decreased now than what it was before in GF. Okay. But df prime SV is equal to df prime SU plus 1, because suppose this is the shortest path and UV is the edge. Yeah, UV is an edge in the shortest path. I mean, you could even be S for all you care. But and then just by the shortest path property, we have this. Okay, but I know that this is greater than or equal to df SU plus 1. Why? So why is this? So why is df prime SU greater than or equal to df SU? Because the assumption is that V is the closest to vertex from S where this violation happens. So which means for U the violation does not happen. So for U the claim is true. So let me capture that. The subclaim. Okay, so for here df s f prime SV is less than, this is the claim. Now I want to claim that this edge UV is not in GF, right? In GF, this edge is not there. Okay, suppose not. Then in F, in GF, SV is less than or equal to DF SU plus 1, because the length of the shortest path from S to V is at most length of the shortest path from S to U plus 1. Maybe there is even a direct path without the edge UV, but if UV is there, I know that I can say this. Okay, so now I want to somehow, I have some contradiction out there, because okay, so this is less than or equal to df prime SU plus 1, because for u in f prime the distance only remains the same or increases, and df prime SU plus 1 is equal to df prime SV, which is sort of a contradiction, because we just, what we have shown is that df s in f the path was actually less than or equal to in f prime, but our contradiction was in f was it's greater. Okay, so I'm going to say okay. So what I'm saying is this edge UV is not in GF, but it is made it in GF prime. How did that happen? We discussed this before, that the edge VU was probably, not probably, definitely in the shortest augmenting path, right, in GF, because if UV was not before, it was saturated, now it has made it in GF prime, means that therefore VU is in GF, therefore DFU is less than or equal to SU. Okay, I could have omitted S also. Now again we will get some contradiction. From whatever is on the board. Okay, so this is just some it's actually not even equal to, it's exactly equal to, because this is part of the shortest path. We are always doing shortest path augmentation. So DFSU is equal to DFSV plus 1, and DF prime, which we have here, is greater than or equal to so it turns out actually if VU was actually part of the augmenting path, then the distance from S to V would have actually increased by at least 2, though we assume that it actually has decreased. Okay, that's a contradiction. So that proves, so this is a contradiction to the assumption that df prime SV is strictly less than the distance from S to V in F. Okay, so what this is saying is the shortest path either remains the same or increases between from S to any vertex. And now lemma 2, again, bulk of the proof is actually here, that an edge is critical at most n by 2 times. Why? Okay, I'm going to use this more or less the same proof. So Okay, so here was F and here was GF, where this edge UV was critical. UV became critical, and later on it's becoming critical again, right? I want to say that between these 2 points, the distance from S to U or V, we'll see, would have actually increased by at least 2. More or less the proof is here. Okay. And I know it starts with 0. The distance from S to U cannot go more than n minus 1, and it's increasing by 2 all the time between 2 points of criticality. So it won't go, it won't be critical more than n by 2 times. And why is this true? Again, if UV was critical, UV went away from residual network, and it is surfacing again means that there is some other flow F prime where, so it need not be here, but maybe in some other F prime where you augment it through VU. And basically work through F and F prime, I think would play this role here. You will see that the distance from F prime in F prime from S to V or U, I don't know. Okay, we'll see what. Okay, so I'm going to erase this. Is this clear that it was critical and then it's becoming critical again means that some other flow F prime for which there was a reverse flow from V to U sent. Okay, so let me just argue with this that we have distance from SV is df is U plus 1, and in F prime SU is equal to df prime S V plus 1. But we know from lemma 1 that the distances are never decrease. So, okay, this is greater than or equal to df SV plus 1, and df SV is df SU plus 1. So, this is equal to, so distance from S to U increases by at least 2. Between 2 points where the same edge becomes critical, the starting point of the edge distance increases by at least 2, so it cannot become critical more than n by 2 times. Okay, so that completes the proof that this algorithm, if you augment through shortest paths, the number of augmentations you do is at most mn, and each augmentation costs you order m, so totally it's an m square n time. Okay. Now there are a lot of other heuristics on augmentation. You can augment by in parallel a number of paths, and hence you can increase the flow by a lot, and there are several such things, but we won't, maybe you can look at it in some exercises. Now I want to talk about a different kind of algorithms, different from Ford-Fulkerson type algorithm. So Ford-Fulkerson type is a very generic thing that as long as you have some augmenting ST path in the residual network, you can augment, right? Just keep doing it. Whereas this is a different kind of algorithm, so we will. So these types of algorithms are called pre-flow push or push relabel algorithms. So we will actually reverse engineer sort of optimality here. Okay, so if you think of Ford Fulkerson, at any point of time we had a flow. We always had a feasible flow. And when did we reach optimality? When the residual network has no path. Okay, no, residual network has no path. That's when I reach optimality. In these type of algorithms, we are going to maintain the fact that residual network has no path. Okay, because that's where we want to get to. So we will maintain that. But what we will not have is a feasible flow. We gradually move towards feasibility. When we reach feasibility, we know that we have reached max flow because okay. So what we actually will have is what is called pre-flow, not a flow. What is pre-flow? This is again a function f from E flow. So and f of E is less than or equal to capacity of E. That's it. We don't care about the conservation constraint. But we do care. What do? We ensure that summation flow in to a vertex minus flow out for all V in V minus S. We just ensure that this is greater than or equal to 0, not necessarily equal to 0. That what is coming in is at least what is going out. Okay. Of course, for S, everything is going out, so we don't care about S. So this is called a pre-flow, right? It just violates. It could violate the conservation constraint. I don't have equality, but I will start with pre-flow and eventually reach a flow, and that's when we have optimality. Okay. So this is pre-flow. What is a starting pre-flow? Right? In Ford Fulkerson we had a starting flow where all the flow edges 0, right? Because the capacities are all non-negative. You satisfy constraint both constraints. Here the starting pre-flow or initial pre-flow is essentially saturate edges out of S. That is F S V equal to the capacity and is 0 for okay. So it's a pre-flow, right? Because it satisfies the capacity constraint, because for edges coming out of S, I've just fully saturated. For the others, it's 0. And for every vertex, what is coming in minus what is going out is greater than or equal to 0. So it's only for vertices directly in reachable from S. There are more coming in, nothing going out. For everybody else, is nothing coming in, nothing going out anyway. Okay. So let's call this as excess at vertex V. Okay. So our eventual goal is, so every vertex has some excess. If all the excesses are equal to 0, then we have a flow, right? We are done. And so our goal is that look at vertices that have excess flow and somehow try and push that excess flow through some edges. That's the goal. Okay. But we are going to do it very carefully, push them, because see eventually I mean, this may not be the max flow. You may not be able to push everything to T, right? Because max flow may be less than summation CSV. So we will push something back to S. Whatever you can't push, you will push it back to S. Okay. So the way we will push it is using a careful strategy of using what is a height function on the vertices. Okay, you could also define residual network exactly the way we define for flows. Right? So you can say GF and edge UV is in the residual network if FUV is less than its capacity or FVU is greater than 0, right? The fact that F is a pre-flow should not be a problem. We just define this residual network. And notice that there is, for this initial pre-flow, there is no ST path in the residual network. Why? All edges out of S are not there at all. No edge out of S is there in the residual network. So there is no ST path. So this is some property we will maintain throughout. But we will maintain throughout using what is called a height function. So let me define. So the height function is on the vertices. H of S is n. And for all, this is sort of the invariant we will maintain in the residual network. Okay, so let's call this. So initially, so this is sort of the invariant property of the height function, and initially H of S is n and H of U equal to 0 for all U not in S. Yeah. So somehow think of this excess as some excess liquid which you are trying to push it, and we will push it from a higher vertex to a lower vertex. So that's what this height is defining. Okay. So we will always push from some higher vertex to a lower vertex. And if you can't push it, you will keep increasing the height of the vertex. And anyway, so if I have a vertex where I can't push to anybody, I still have excess, then I will increase its height and see whether I can push it. Eventually, its height might go above the height of S and push things back to S. Okay. Okay. So first of all, is it clear that this initial height function satisfies this condition with respect to the initial preflow? What is it I want to ensure? That for every edge in the residual network, height of U is less than or equal to height of V plus 1, right? Height of S is the only thing which is high, very high. So you only need to worry about edges going out of S in the residual network, because then height of u is large, this is small, and you have a problem. But thankfully, no edge out of S is in the residual network. Okay, good. This is the setup. Now, like our Ford-Fulkerson algorithm, there is some generic algorithm which we will define what to do, right? So we're just going to get rid of the excess out of every vertex. So that's the goal. Okay, so there are two operations which you do: push and relabel. Let's see, what does you're going to push through the edge UV. When am I going to push through the edge UV? What are the conditions I need? I should have some excess flow at U. I should have some residual capacity on the edge, right? Or yeah. And I'm going to insist on one more condition on the height, where height of U is equal to height of V plus 1. If this happens, I am going to push through that edge UV. Okay. So, always I am going to push from a higher vertex to a lower vertex. Well, more precisely, from a vertex whose height is exactly one above the lower vertex, the other vertex. That's when I am going to push. Anything above actually, I won't, they are not even part of the residual network. So, I won't even have a residual capacity, right. So, if you think about height, so I have a vertex U at this height, and there is something, nothing else, and suppose V was at this height, right. So, this is, then this edge doesn't even have a residual capacity because of this condition. Because what am I saying? That if there is a residual capacity, means that height of U either is same height as V or below, or it can at most be one more height, right. So, if for such an edge there is no residual capacity anyway, and now I am saying you can do a push if height of U is more than exactly one more than height of U. In this case, I will push. How much do I push, or what is the result of it? Clear, right? You know what to push. So, what happens? That f of uv now becomes whatever the original f plus. So, here is an edge. So, forget about the height condition. This is for a technical reason. We'll use it to prove all that. But all I am saying is, I have some excess. Here is an edge which has a residual capacity. I am going to push. How much can I push? How much flow can I push? Min of whatever residual capacity available, I will push that much. I may not even have that much excess. So, it is a min of these two quantities, I will push it. Okay. Now, more things get updated here, because the excess at V will increase now, and excess at U will decrease now. Whatever. This is my push operation. Okay. This is one way to get rid of some excess. Okay. But what happens that I have some excess, but I have nothing to be able to, for every edge in EF, it so happens that height of U is less than or equal to height of V. Nothing is one more. What do? I increase the height of U. We're almost done with the algorithm. So what is the other operation I'm going to do? Relabel. When does this apply? I have x's, and for all uv in the residual network, height of u is strictly less than or equal to height of v, right. I know that it's strictly less than or equal to height of v plus 1, but nothing is at one level above. They are all of the same level or below. So, I can't push anything. So, what I will do is I am going to increase the height to 1 more. I may not be able to push again, keep increasing it. Well, when, how much can I increase to? I am going to increase to minimum of HV or 1 plus okay. So, after the initial pre-flow, my goal is to get rid of the excesses at vertices and make the whole thing into a flow, and then I will argue that actually I have reached optimality. How do I get rid of the excesses? Well, I will see if there is some edge I can find to push. Okay, I want that edge to satisfy these conditions. This is the critical condition. If you can't push because of the height condition, I will actually increase the height. Now I will be able to push to somebody, because as the residual capacity is available and my height is 1 more than somebody. So, I will push will apply. So, now my algorithm is initialize pre-flow and f and height function h. I have told you what is the initial height function is. I told you what the initial pre-flow is, that saturate edges out of S. While there exists V such that excess of V is greater than 0, push or relabel as applicable. That's it. Right? I mean, you have to do the careful implementation, which vertex to choose and so on, but those are details. But when I have an excess, see if you can push. If not, increase your height, relabel, find another vertex which excess, keep doing it until your excesses all vanish. Then you have reached a flow. So, now I need to argue a lot of things. This is the whole algorithm, right. Now, I have to show that this algorithm does not get stuck, that some excess is greater than 0, but I cannot apply these two conditions, or that it does not go into ever, there it will actually terminate. I want to understand how much time it takes, all that. Okay, algorithm clear? Okay. So, what are some easy things to observe? That that if you have a vertex whose axis is positive, okay, let's write down some lemmas and stuff and prove them, right. Claim if EV for a vertex is greater than 0, push or relabel applies. So, it does not get stuck, that there is something you can do, right. Is that clear? That if you can't find, I mean, excess is greater than 0, but I can't find somebody in my residual network, or my height is less than or equal to HV, then I can't apply push, but I claim that in that case I can apply relabel. Right? Is that clear? What do I have to, anything to be proved? Something has to be proved. What has to be proved is that, okay, so if push doesn't apply, that means for any edge out of U in the residual network, I have HU is equal, is less than or equal to HV. So I find the minimum and then sort of increase it. Then I know that whatever that height, I am one more than that, so I'll be able to push something into it. Okay. Only thing I have to show is that why is this set? Why should there be an edge out of U in the residual network at all? Okay, you can do some calculations, but excess is strictly greater than 0. What does that mean? There is more flow coming into it than flow coming out of it. There must be some edge coming into it with a non-zero flow, right? So that edge, the other direction must be in the residual network. So this set is non-empty, and so push or relabel applies, right? Good. Okay. What else I have to show? Height function is maintained all the time. At all times, F is a preflow and H is a height function. Right? So preflow means that it satisfies the capacity constraint, and height function means that it satisfies this constraint. Okay. But this is easy to see that we actually, preflow is easy because I never push anything more than a capacity. I just have to satisfy capacity constraint. But to argue that you actually satisfy height function, you have to do some case analysis, but that's property of the algorithm. That's the way. Height of S and U never change. Sorry, height of S and T never change, but okay. There are only two operations we'll do. So let's verify that. When I am pushing, what happens? Height. I'm not really changing the height of any vertex, but some reverse edge may get into the residual network which was not there before. So I need to ensure this condition. Okay, but you can verify that so height of U, height of V, height of U is equal to height of V plus 1. That's when so this is my height scale, and this is when I am pushing through this edge. Heights don't change. This edge may go away from the residual network, so one constraint is gone, but this edge may come in, but that's okay. What do I want? I want height of V to be less than or equal to height of U plus 1. Sure. Height of V is actually is equal to height of U minus 1 actually. So that condition is satisfied. So when you do push operation, this is satisfied, the height condition is satisfied, and when you do relabel, you are increasing the height of a vertex, and you are doing it carefully, min of this, right? So for any other edge, it's still less than or equal to. For one edge, it will be equal to, and for any edge coming into it, no problem. You are only increasing the height of this vertex. Okay. So, but you need to argue all of this carefully. Yes. Okay. Good. Here is my important claim. There exists no ST path in GF at any time. Okay. Throughout my algorithm, if you just go and find my residual network and look at the residual network, I claim there is no ST path. Why? Because of this height function, because it's all here. Because if there is an ST path, right, suppose there is, and suppose it is S V1, V2, Vk, T, where k is less than or equal to n minus 2, because n is the number of vertices including S and T. So, suppose there is such a path, but you know that for any edge in the residual network, you know height of u is less than or equal to height of v plus 1, right. So, height of S is less than or equal to height of v1 plus 1, less than or equal to height of v2 plus 1, and so on and so forth, so forth. It's, so height of S is less than or equal to height of T plus k, right. Height of T and S, they don't change. Height of T is 0, height of S is n, and you get k is greater than or equal to n, but k is less than or equal to n minus 2, contradiction. Okay, so just this property ensures that there is no ST path. Okay, good. So now I just have to tell you that the algorithm terminates, because then when you terminate, you actually have a max flow, right? Why? If the algorithm terminates, you actually have a max flow. Why is that? Because all the x's are equal to 0. So what you have is a flow, and there is no ST path in the residual graph. So you've got max flow. So now all I have to tell you is that algorithm will actually terminate, and and give a running time bound. So we will do both together. So I'll actually give a running time bound, so that will also prove that it will terminate. Right? So the corollary is that when, or if and when the algorithm terminates, and the proof is that E of v equal to 0 for all v, so it's actually there x is a v in v minus s. So f is a flow, there is no ST path in GF, so f is a max flow. So, you know, we were sort of greedily pushing our initial pre-flow or saturate whatever you can from S, right? Eventually that may not be the max flow. So now what is happening in the algorithm is that the excesses are pushed, but if it cannot be pushed all the way to T, what happens? You know, some vertex height will go beyond n, because S's height is n. Some vertex height will be increased beyond n and pushed back to S. Okay, so now okay, so what is left is runtime analysis, right? So what we will do is we will just bound the number of pushes and number of relabels done by this algorithm. That's all we'll do. Now, After that, there is some little work left to carefully implement it. Set up some data structure, some V, and look at vertices in some order. Do all that, but that can be done. Okay, we'll come to that later. So I will bound the number of pushes and relabels. So to push the number of relabels, what is the relabel algorithm doing? It just realizes that push is not possible. Push, given my current height, increase the height. Okay. Today we will bound the number of relabels is to show that the height of a vertex, that will show that number of pushes, number of relabel operations is bounded by something. Okay. Next claim. So at any point, right, you have some pre-flow, and I have an excess at some vertex. Then I claim that there is a path in the residual network from this vertex to S. Is that clear? Is it intuitive? See. How did I get excess? Who gave me excess? Yeah. Everything comes only from S, right? From S, I got some excess. So in the reverse direction, the residual graph will have a path, right? So okay, so a formal proof, well, sort of semi-formal proof is let U be vertices reachable from V in GF, right? So in my residual graph, I have a vertex which has an excess, and I'm collecting all vertices which I can reach in the residual network, and this is my U. And suppose S is not in U, right? So this is my U bar, and S is sitting here. Now, if I compute summation E x's of V, where V in U, what is this? Right? This is x's is flow in minus flow out, right? So if I compute for every vertex here, V is a vertex here, but for every x, okay. For every vertex, I just compute its x's, sum of the x's. What would it be? I mean, within inside, so if you have an edge here, that flow here would be counted here, and in the out of here, and this will be counted in the in of this, so sort of they will cancel out, right? So what it would be is the flow from U bar to U minus, right? You can verify this, that look at all the edges coming in from U bar and look at the flow in them minus the flow going from U to U bar, because anything inside will cancel out. But you know that this is greater than 0, right? Why? Because V is sitting there and its x's is positive, and everybody other x's are greater than or equal to 0, because we have a pre-flow. So this sum is strictly positive. So you have at least an edge coming, I mean there is some edge where there will be some positive flow here, okay. So that means in the residual network, that reverse edge will be there. but you told me that S is not reachable from V, but actually S is reachable from V, a contradiction. Right? These are supposed to be all vertices reachable from V, so there cannot be any edge in this direction at all, but there is. Right? So this implies that, okay, the proof of this, I'm just leaving it as an exercise. You can do the cancellation, verify. So there exists an U in U bar, V in U, such that FUV is strictly greater than 0, implies the edge VU is in GF, but V is in U and U is in U bar, a contradiction. So S must be in U, so you can reach, that is, okay, that proves the claim. Right? Okay. So now a corollary is EV is greater than 0 implies its height is at most 2n minus 1 or 2n minus 2. We'll see why. Why? Because height function has the property, right? So we know that there is a path from V to S in the residual network, and height of S is n. And so in this path, you know that height of this is less than or equal to height of this plus 1. So height of V is less than or equal to height of S plus, if you call this V1 to Vk, is this path. So height of V1 plus 1, so Vk plus k, and so height of S plus k plus 1. But k is less than or equal to n minus 2. So it's at most 2n minus 1. So another corollary now is number of relabel operations by the algorithm at most for each vertex, each relabel operation increases the height by at least 1. It might do it one at a time. It starts with 0, goes all the way up to 2n minus 1. Do it for every vertex. So this is at most 2n minus 1 into n minus 2, right? Because you can only increase the heights of everything except S and T. Okay, so I bounded the number of relabel operations. Okay, so now I have to bound the number of push operations. So let's do So let me divide the kind of pushes into saturating push and non-saturating push. Okay. What does the push operation do? It finds an edge where the height condition is satisfied. There is a residual capacity and I have an excess. I will just push whatever possible through that edge. Suppose it saturates the edge, then I call it a saturating push. If it doesn't saturate the edge, I call it an unsaturating push. Okay. So which is easy to bound. Let's look at unsaturating pushes. Okay, I think I can finish the proof. I was just thinking. So unsaturating push means that the edge through which flow is pushed is not saturated. Okay. No, it needs an argument. Okay, so maybe I'll argue the bounding the number of pushes next time. So the claim, because I don't think I'll finish in 5-10 minutes, it requires a few more minutes. Let me just claim next time the number of pushes is order mn square. So this is n square, and number of pushes you will bound it by mn square, and it'll be like, it's an interesting potential argument. We'll come up with some potential and see how this is increased, decreased by various operations. Now recall what was the algorithm, running time of Edmonds Corp algorithm? M square n, right? Because we just said that every edge is critical some order n times. So number of augmentations is m times n, and the time for each augmentation is m, so it's m square n. But this algorithm improves it to mn square, right? This is a better algorithm. So we'll see an argument for why the number of pushes is bounded by this, how do we implement this, and we can actually even improve this to order n cubed by a careful choice of what pushes and relabels to do. Okay, I think I will stop. Some of them, yeah, we don't need too many of these claims to prove this, but yeah, next time.